Hello, this is Mrs. Scuffle, and in this video I'm going to review Lesson 2 of Unit 1. In this particular lesson, we looked at a quadratic function and its inverse. To put the context of this particular lesson, we had a Ferrari and we had the function for its braking speed. The function was d of x equals 0.03 s squared, where s is the speed in miles per hour and the d was the distance in feet. Now, to calculate the distance in feet that it would have to brake, we would take this expression, the 0.03, and we would multiply it times the speed squared. So 0.03 times 50 squared is 75 feet. I would do the same thing with the rest of these. 0.03 times 55 squared is going to give us a braking distance of 90.75 feet. So 0.03 times 100 squared is 300 feet. And we were told that the maximum speed of this particular Ferrari was 217 miles per hour. So its braking distance would be, if we take 0.03 times 217 squared, would be approximately 1,413 feet. So now I'm going to graph this information, and I'm going to count my spaces here. I think I can go by tens. Every line is 10, so we're going to start at a speed of 0. Then we have 20, 40, 60, 80, 100, 20, 40, 60, 80, and at the very end here is going to be 200. So this is speed. That was our input in our table. So the distance, I'm going to go by 50s, I think. So every line is 100. So 200, 400, 600, 800, 1,000, 1,200, 1,400, and we'll see what this graph looks like. Well, at 0, if the car isn't moving, it isn't going to have any braking speed, so that's where it's going to begin. And we have at 50, we should be at 75. At 100, we should be at 300. I should say 100 miles per hour, we should be at 300. I didn't try it at 200, so I'm just going to go ahead and put 200 in to my calculator. 0.03 times 200 squared puts us at 1,200. So when I graph this, you'll see that we have a curve that keeps increasing, and it increases faster and faster over time. We call this an exponential, or this is actually a quadratic function, excuse me. This is quadratic because of the s squared. So this is what our curve is looking like for this particular function. Now, to remind you, domain and range. Domain is the values for the inputs. And for this particular car, we have a range of 0 to 217 miles per hour. You'll notice I'm using interval notation here because 0 is the slowest the car can go and 217 miles per hour is the fastest it can go. I'm using square brackets here because I know those values. For the range, that is going to be the outputs. What are the values for the outputs that correspond to our inputs? Well, our minimum value in the range is 0, and its maximum, if we look at the table, is 1,413. We can also describe this as, I'm going to just change the color here, it's increasing over the entire domain because it's always increasing. The faster the car goes, the longer it's going to take to brake. Our maximum value comes from the maximum value of our range. And we're going to say that our maximum is 1,413 feet at 217, let me write that again, miles per hour. Our minimum is 0 feet at 0 miles per hour. So these are some of the features that we can describe in the context of our car. Now, what if I want to know what the inverse function looks like? Well, in this case, we need to do some work to undo this. Our first step is, I'm just going to write the initial equation as d equals 0.03 s squared. Then I am going to switch d and s around, so switch the variables. I'm just going to make a note of that. Switch the variables. Actually, no. I'm not going to switch the variables yet. I'm going to leave them just like they are for now. Sorry about that. What I'm going to do is I'm going to undo the equation to get the s by itself. That's what I'm going to do. So to undo this, to get s by itself, I need to undo the multiply by 0.03. So I need to divide both sides by 0.03. Now, I can't actually divide a variable by 0.03, so that's just going to stay d divided by 0.03 equals s squared. To undo squaring something, or to undo something to the second power, you take the square root of both sides. So that means that my function, the inverse, is going to be d over 0.03 equals s. And I'm going to write it now as s of d because we're finding speed in terms of distance. So this is our inverse function of our braking distance. And I'm going to use this function. So we had s of d equals the square root of d divided by 0.03. But since I already had some values from my table, I am just going to take my previous table and I'm just going to switch the numbers around. So we have 75, 50, 90.75, 55, 300, 100, 14, 13, and 217. So let's go back to my table. We have 75 feet at 50 miles per hour. We had 90.75 at 55 miles per hour. We had, I need to double check, 300 at 100. We had 1200 at 200. And we had the 1413 at 217 miles per hour. So this time, instead of speed being my input, distance is my input. And my speed is my output. So that means I'm going to also change the scales that I used. So every line is 100, 200, 400, 600, 800, 1,000, 1,200, 1,400, and just double check the scale I used. I went by tens, so my speed, I'm going to go by tens as well. 20, 40, 60, 80, 100, up to 200. So we know from before that we're not going to go anywhere if we're not moving. So my graph can start at 0, 0. We had a distance of 75 at 50 miles per hour. We had a distance of 300 at 100 miles per hour. So 300 is going to be up here at 100. We had a distance of 1,200 at 200 miles per hour. And you'll see that we still have a curve, but that curve, while it's still increasing, the amount it is increasing by slows down over time. So here's our curve. So our domain also switches from what we had for our domain before. So instead of 0 to 217, our domain this time is going to be 0 to 1413, and the range will reverse as well, 0 to 217. And that should be a bracket on the 217 because that is the fastest speed. Our maximum and minimum will also change, because maximum and minimum come from the interval for the range. So our maximum is 217 miles per hour at 1,413 feet. And our minimum is 0 miles per hour at 0 feet. And once again, this is increasing over the entire domain. It's always increasing. Now, what if we weren't being held to this domain and range? What if we weren't talking about a car? What if we were talking about just any f of x function? Well, that would be for the entire, all of the x values. So what we would see for d of s, and I'm going to do this one in blue, I'll just or red, I guess, since that's the pen I have on. This would be a parabola that looks something like this. When you have a squared function, that's going to be a quadratic function. We get a parabola. It's a mirror image. It's symmetric around an axis. Well, if we do the replacement, if we do the switching, the inverse, which I'm going to do in blue, is going to look more like this. Well, you can see that if I were to draw in, and I know I'm doing all of this with hand sketches, but if I were to draw in the line y equals x, what you should see is a graph that is reflecting across this line. Well, when we look at the inverse, when our domain of our initial function is all real numbers, our inverse is not a function. Our inverse has two outputs for every input with the exception of the vertex. So that means that the function for the domain of all real numbers is not invertible. In order for it to be invertible, our inverse would also have to be a function. So we would have to restrict the domain. So to make the inverse invertible, I'm going to make a note here. To make the inverse invertible, or to make the function invertible, that is, to make the function invertible, restrict the domain. Let me spell this correctly. Restrict the domain to the values x greater than 0. If we do that, if we go greater than 0, it would just be the right-hand side of our parabola, and we would just have this top side of our square root function. So the inverse of a quadratic is a square root function. When you have a quadratic function, you need to restrict the domain in order to make it invertible, in order to make the inverse also a function. So takeaways from this particular lesson: the inputs and outputs of the tables are switched, just as they were with our linear functions. The domain of our function is the range of its inverse, and vice versa. So the domain and range of the function switch when they become the domain and range of the inverse. And a quadratic function is not invertible unless the domain is restricted to one side of the parabola. And we generally restrict it to where the input values are positive. And this concludes our review of Lesson 2 from Unit 1.